Okay, so in this video I'm going to show you how to solve a undamped system subject to no external force. So the equation of motion is presented in here, and we also know the initial position and initial velocity. So how can we solve these ODE? So the first thing is we assume a general we assume that your solution X is in this format, E lambda T, okay? And then based on this assumption, we can plug this X back into the original equation. So mx double dot equals to A lambda twice E lambda T, because you have to calculate time derivative twice, so the coefficient before t has to be printed in front twice, and then kx is a k E lambda T, and then we can put these two together. Oops, I forgot the m here. So a E lambda T equal to 0. So we can collect the common terms. So we have m lambda square plus k, and then the a E lambda T equal to 0. So these equations stands at any time point t. Okay, so that's why in order to allow these equations exist, we have to make sure m lambda square plus k equal to 0. And then we can solve these equation very easily. Your lambda equals to positive minus k over m j. So your solution of lambda is a complex number. So we usually define omega n, or the natural frequency in radian per second, as k over m square root. So by doing so, your lambda is positive minus omega n j. So once you find your lambda values, the second step is we assume a general solution. So your general solution is xt equals to a1 ej lambda 1 plus a2 ej lambda 2. So lambda 1 and lambda 2, they're the solutions of lambda, and a1 and a2, they're constants. Okay, so these constants, they are related to your initial conditions. Related to initial. So currently we don't know what a1 and a2s are, but once we plug in the initial conditions, they can be determined. All right, so let's write it out. So we already know that the initial position at t equal to 0 is x naught. And then let's plug t equal to 0. Oh, I forgot one thing. We need to put a t in the exponential index as well. So let's plug t equal to 0 back into the equation. We have a1 plus a2, because e power of 0 is just 1. Okay, and then we also know the initial velocity. So that means we have to calculate the velocity first. That's first order derivative, and it becomes a1 lambda, oops, so after finding your lambda solutions, the second step is we assume a general solution of xt. So we know that this xt is a1 e lambda 1 t plus a2 e lambda 2 t. So lambda 1 and lambda 2, they are solutions of lambda. Two different solutions of lambda. We already find it out in the previous step. And a1 and a2, they're constants to be determined, but they're also constants related to initial conditions. All right. So we know initial position and we also know initial velocity. So that's why we have to find out what's the general solution for velocity. It's just dx dt, and then it becomes a1 lambda 1 e lambda 1 t plus a2 lambda 2 e lambda 2 t. So we have both the position and velocity now. So let's recall the initial condition. So we know the initial position at time equal to 0 is a1 plus a2, and these two, a1 plus a2, should equal to the x0. That's because your e to the power 0 equals to 1. And then let's look at the initial velocity. So x dot time equal to 0. That gives us a1 lambda 1 plus a2 lambda 2. That equals to v0. And we already know the value of lambdas, so we can put it in. So we have, so either case, in this case, we can assume lambda 1 is omega nj, lambda 2 is omega nj minus. So the order of these lambda 1, lambda 2 doesn't really matter. So let's plug it in. We have omega nj a1 minus a2. All right. So after that, we can solve the equation and to find out a1 and a2. So let's see. Your a1 is, so to solve these equations easily, you can move these omega nj term to the left hand side, and you would have a1 plus a2 equal to x0, and a1 minus a2 equals to v0 over omega nj. And then equation 1 plus equation 2, you have 2a1 equals to x0 plus v0 omega nj. And equation 1 minus equation 2, you have 2a2 equals to x0 minus v0 omega nj. All right, then you find your a1 and a2. And you can move these two to the other side. Your a1 is just 1/2 of this. Your a2 is 1/2 of this. Okay? And after that, you can plug your a1 and a2 back into your xt. But we usually want to write your x. Oops. We usually want to find our xt in the format of a standard sinusoidal equation. Okay, so how can we get from the exponential expression to the sinusoidal equation? So we have to use Euler's equation. So that means, let's see, your xt equals to a1. Let's replace the lambda 1 by omega nj. And then your lambda 2 is minus omega nj. So based on the Euler's equation, your e omega nj is just cosine, oh, I forgot the t, sorry. So it's cosine omega nt plus sine omega nt complex number. and then A2 cosine omega nt minus j sine omega nt. Alright, so then we also collect terms. Your A1 plus A2 cosine nt plus A1 minus A2 j sine omega nt. Alright, so that means we just need to find out A1 plus A2 and A1 minus A2. That's actually directly given in these two equations, 1 and equation 2. So let's replace it. That's x naught cosine omega nt plus v naught over omega n sine omega nt. Okay, so how can we, so right now in this equation we have both cosine and sine in the equation. How can we merge them to form a single sine? So the idea is, if you find a triangle, this is our angle 5, and then this is our x naught, and then this length is v naught over omega n. Okay, so that gives us sine omega nt plus 5 times a. The big A, let me use a different color, red. So this length is your amplitude A, and this angle 5 is your phase lag. Alright, so then we can easily identify A and 5 from this triangle. So that's x naught square plus v naught over omega n square, and then the 5 is just invert tangent x naught omega n over v naught. Cool.